Hi, I'm Mindy. I did my thesis on an optimized satellite constellation for bushfire detection. Bushfires have been commonly associated with Australia since the beginning, but with the changing climate and increasing surface temperatures, the fires have recently grown in intensity as well as damages. So looking at figure 1, you can see that the 2019 bushfire season has burnt out the largest area of the country so far. In fact, the 2019 to 2020 fires have destroyed more than 2,000 houses, burnt off 100,000 square kilometers of area, and killed or displaced nearly 3 billion animals. So figure 3 is an ideal representation of the motivation behind our thesis. Our goal here is to detect bushfires efficiently and at their early stages so that a disaster like this could be avoided in the future. So our path to achieving this has 4 steps. First, we plan to develop a constellation with constant coverage of Australia, and then to equip the satellites in this constellation with sensors that could see even the smallest bushfires. Thirdly, we plan to use on-orbit image processing to detect bushfires online, and lastly, to use edge computing and parallel processing to use several satellites to detect bushfires. So when designing the constellation, we looked into optimizing 3 different parameters. First, our area of interest was the coastal area, as the central Australia does not have much of a forest. So we divided up this area into grid points separated by 0.5 degrees latitude and longitude. So if our constellation had good visibility over this area of interest, it would also cover a lot of these grid points. So we wanted to maximize speed, the number of points covered. We also wanted to minimize the number of satellites, and as launching a satellite is an expensive process. And lastly, we also wanted to minimize the revisit time R, as we want more satellites to visit our area of interest more often. So now this is a multi-objective optimization problem. We analyzed the efficiency of using 2 different algorithms for the final constellation generation. And we discovered that while they both gave us similar results, CNSGA2 was much faster. So we ended up using that for our final constellation. We also tried formulating the constellation in 2 different ways, and we discovered that formulating the constellation as a whole instead of as individual satellites gave us higher coverage using less satellites, so we ended up using that for our final constellation as well. So next, we wanted to choose a sensor that could see even the smallest bushfires. The sensor on board Rapid Eye was ideal for this, as it had a pixel size of 5 meters. It also had a considerable field of view. So we chose this to be our sensor on our final constellation. So here is our constellation outcome. This has 100% coverage over the area of interest and 75.4% coverage over the middle section. It can generate a new image of our area of interest once every 6 minutes, and it can generate a new image of the rectangular Central Australia once every 10 minutes. So now we can see early stage bushfires, but we still can't detect fires fast because we still have to send our images to ground to be processed. So a solution to this is doing image processing on board. So we follow this process of which can be simplified by choosing each pixel, calculating their radiances, separating the pixels by land and sea, and extracting the land pixels and using thresholding to discover where the potential fire pixels lie. So here are more results obtained using the same algorithm, and the blue dots show confirmed fires, while the red ones are the detected ones. And the overall accuracy of this algorithm was 83.06%. But we still can't detect fires efficiently because satellites don't have the best processors. The state-of-the-art radiation-hardened RAD 750 processor only has a processing speed of 200 megahertz, which means that it would take 2.20 seconds to detect a bushfire from a single image. So to solve this, we use edge computing. Edge computing is this idea that doing a processing near the source of the data itself can save time and cloud storage. So here we use it to do image processing parallelly among several satellites. So to do this, we need an inter-satellite link. We use a GSO satellite in an orbit similar to Optimised D3 because it has a constant coverage of Australia at all times, as well as a constant coverage of 90% of the satellites in the constellation. So the steps involved in this process is as follows. First, the satellite takes an image of Australia, and it takes the reflectance and radiance data of each pixel and sends that data to the GSO satellite. The GSO satellite then selects potential edge nodes or satellites and sends the data to them. And each of these satellites process the segment of data they have received. And if any of them detects a bushfire, this sends the bushfire detection coordinates back to the geostationary satellite, which then notifies the ground station. So adding up all the times required for this process, we can see that using 20 edge nodes or satellites, we can detect a bushfire with 1.39 seconds. So this is much less than the time taken for one satellite. So with this, we have achieved both of our goals. So to conclude, bushfire detection requires high resolution sensors, which comes with low field of view angles. This means that a lot of satellites are required to detect bushfires in real time. And image processing on orbit can reduce the fire detection time, but only if the processing is divided among several satellites. But the power requirement for this distributed processing may be larger than the power required for a single satellite. In terms of future work, using a hybrid algorithm to generate a constellation or using machine learning for image processing would be ideal. Thank you.